So Max said that he had gotten as far as number 4. I'm going to take a screenshot of this. Maybe. This button, this button. Shoot. I think I'm still failing. There, that's a screenshot. So now, let's just add a sheet. Portrait is straight up, right? The terms bedevil me. Actually, I forgot I have a shortcut to it, but too late now. Must be that one. Seriously. Okay, I think we're at the top of the screen now. No. Okay, I'm failing. Let's just do it. Let's not play Richard Roulette. So number 4, a light bulb radiates most strongly at 3,000 nanometers. How hot is its filament? When you're solving these problems, of course, the first place to start is always, what's the idea going on here? Right? Astronomy is a physics class, and physics is about trying to figure out what things are going on. So we talked about last class period the relationship between temperature and wavelength. In fact, we did a calculation for what my body temperature makes the peak wavelength. So this is the same thing. Does anybody remember the name of the law that relates these? Yeah, Wien's law. It starts with W, Wien's. Just like my family name is Wien, W-E-E-N, but his is W-I-E-N, because he's German and we're Norwegian. It's the Norwegian family name this week. Okay, so a light bulb radiates. We're going to use Wien's law, which says, that's the relationship between the peak wavelength and the temperature. So in this problem, we're looking for the temperature. So the first thing I need to do is solve this equation for temperature. Now you can find it written both ways. I wrote it this way, so I would be able to do the solving because, of course, some people, math is not, a language they're fluent in. Much like Spanish for me. We're trying to learn Spanish since my son's taking it in high school. Yeah. Without a textbook using Duolingo, I don't think that's the best move. He's telling us, there are rules. Really? Okay, so to solve this for temperature, right now temperature is in the denominator. I want it in the numerator. So I'm going to take both sides of the equation. What you do to one side, mathematically you have to do the other. So I multiply both sides by temperature. Why? Because now I'm going to cancel temperature on the right side, and on the left side it'll be in the numerator. But then I have temperature multiplied by wavelength, and I want temperature by itself. So if temperature is multiplied by wavelength, how do I get rid of the wavelength there? Divide, yeah. So I can divide both sides by the wavelength max. That was bad. And so now I have my equation that says, stop that. Well, I got it to move again. There's an undo button. So now I have it at, and I'll change to purple, temperature is equal to 2.9 times 10 to the 6th nanometers times Kelvin over the wavelength max. I'm going to put the wavelength max into my equation. So I'm going to put in, stop that. My palm, I think, is what's selecting. 3,000 nanometers. Now let's pay attention to our units. On top, I have nanometers times kelvins. On bottom, I have nanometers. So those units cancel out. And I have 2.9 times 10 to the 6 over 3 times 10 to the third. So, hey, I got a calculator here that I think will work. Much better than what I had before. I do that calculation, I get 9.67 times 10 to the, if I make the top, let's make the top 29. If I make it 29, that's going to be 29 times 10 to the fifth. The bottom 3 times 10 to the third. 10 to the fifth divided by 10 to the third. How do you do that math? Yeah. How do I do 10 to the fifth divided by 10 to the third? Subtract the exponent. So that's going to be equal to 10 to the 5 minus 3, which is 2. So times 10 to the 2 kelvins. Of course, 9.67 times 10 to the 2, there's a simpler way to write that. 967 kelvins. So now I know, Max, you said you already had that one done. But that was the beginning of what we did from the last class period. Oh, come back into focus. Okay, so the next one. Explain the physical meaning of a transition from n equals 1 to n equals infinity. Remember we talked about that last class period? What does it mean if n is equal to 1? What do we call the energy state for n equals 1? Close. The ground state. Now, I have to, it's the ground state. N equals infinity. What does it mean if it's n equals infinity? It is at zero energy, it's free to escape. That's what that means. So if it goes from n equals 1 to n equals infinity, that means the electron was taken from the ground state up to the point where it's free and it leaves the hydrogen atom. So for hydrogen, calculate the energy associated with it. Okay, that we didn't cover yet. So let's see if I have, I have it right here. This is the slide I think that we ended on. The energy for hydrogen, for electron hydrogen atom is shown here. Now the units shown here are actually odd units. Especially here because I cut off the rest of this equation. Should be minus 2.18 times 10 to the minus 18 joules. Not sure what happened there. So I can take the energy level, if n is equal to 1, it's going to be 2.18 times 10 to the minus 18 divided by 1. We can all do that in our heads. You don't need a calculator. What's the energy if you're in the n equals 1 state? Negative 2.18 times 10 to the minus 18 joules. There's another way we write this. I'm looking at this and I'm feeling really uncomfortable because the units we always use are not joules. Joules are the standard unit of energy. But we actually usually write this as minus 13.6 electron volts over n squared. Just a lot more comfortable with those units. It means the same thing. So in your answer, if you have minus 13.6 electron volts, or if you have the minus 2.18 times 10 to the minus 18 joules, it means the same thing. They're both correct. So why do I prefer the electron volts, as does every physicist? Why do you think?
Easier.
It's easier to write the number. You don't have times 10 to anything. Okay, what about if n is infinity? If n is infinity, what is n squared? It's also infinity. And if I have some finite number divided by an infinite number, what does that equal? 0. So the energy in the infinite level is 0. And that 0 energy is the dividing line between being bound and being free. If it's negative energy, it's bound. If it's positive energy or 0 energy, it's free to go bye-bye. So in terms of energy, we can calculate the energy and we can see, the energy difference had to be, Going from minus 13.6 electron volts to 0 electron volts is a 13.6 electron volt rise. Now, from what we've learned, what can you tell me about the photon that comes in that will give an electron 13.6 electron volts? The energy of a photon is HF. So if it's going to give it that energy, the photon itself has to have that energy because the entire energy of the photon is absorbed, not just part of it. And the photon can only be absorbed if the electron is going to go from one allowed state to another allowed state. Any free state is allowed. So any energy above 0 is allowed. So that means any electron with an energy that's 13.6 electron volts or higher will be absorbed. If its energy is less than 13.6, it's going to have to match a gap. And we're actually not going to do that lab tonight. It probably would have been timely, but I didn't prepare that lab, and it's going to take me time to get it ready, so it's not the one we're going to do. Well, think about it. I could probably get it set up in 10 minutes while you guys are taking a break after we go over this. I'll do that just because it's more timely. It's right on the topic. Anyway, so the photon has to have 13.6 electron volts, which means that I can take this and say, or 2.18 times 10 to the minus 18 joules, and using Planck's constant, I can calculate the frequency has to be the energy over Planck's constant. So let's put in 2.18 times 10 to the minus 18 joules. Divide by the value of Planck's constant. I haven't said it in class. It's just a constant, though. It's 6.626 times 10 to the minus 34 joules times seconds. So now I just have to put that. Now, this is not part of the homework, by the way. I'm going on with the teaching part of class here. I'll come back to the homework. But that's going to be 2.18 times 10 to the minus 18 divided by 6.626 times 10 to the minus 34. And it gives me 3.29 times 10 to the 15th hertz. Now let's bring this back to, is that visible light? The question that gave you the biggest problem as a class on that quiz was the one about which is untrue of light, and a lot of people didn't answer the incorrect wavelength range I gave you. So in any case, it's an area where people, didn't have it memorized. Well, there's a lot of things you don't have memorized. I don't think ill of somebody who doesn't have that memorized. But we had 400 nanometers to 750 nanometers. The reason we used the 400 to 750 was because that, using wavelength times frequency is equal to speed of light, translates to 4 times 10 to the 14th hertz to 7.5 times 10 to the 14th hertz. So visible light is into the 10 to the 14th hertz range. This is 10 to the 15th hertz. What range on the electromagnetic spectrum is going to be if it's a higher frequency than visible light? It's a higher frequency. Remember a word that means higher?
Ultraviolet.
Ultraviolet. Ultraviolet, ultra higher than violet, the highest frequency in the visible range. So this would have to be ultraviolet light, and that's actually pretty harsh ultraviolet light to ionize the electron. Now I'm going to go back to the homework because that was answering the second question. Look at the third one. At its equator, Mercury rotates at 3 meters per second. If astronomers sent a radar signal at precisely 10 centimeters to bounce off of Mercury, what would be the breadth of the return signal? Okay, we haven't talked about that. You're correct. And yeah, we clearly haven't talked about relativity. So these things here, well, those two, just two. Those two are relativity, and we have not talked about those yet. I might take them off the assignment in the end if we don't get it talked about tonight, which is likely. So I'll probably end up taking those off the assignment. So I'll have to go on with the lecture now instead of doing more homework. Okay, we did talk about this emission spectrum. So the energy spectrum of hydrogen. All of the energy levels that we saw, when we had the glasses and we were looking at it was helium gas, but when we were looking at the gas tube, we were looking at energy differences between electrons in a helium atom. Well, the hydrogen atom, and we're going to talk about hydrogen predominantly. I found out that I do still have 2 working hydrogen tubes, but they're with Richard Clark right now. That's why I couldn't find one. But the hydrogen emission shows these pretty colors that you see right here. Now, it's kind of interesting just understanding these. What's going on to make the emission? When I had that lamp up here, do you have any idea what was going on? None? Makes sense. What we had was a tube with gas in it. And so inside of that tube, there's a bunch of little molecules of gas. And then we put a high voltage above and below it, a voltage difference. And what that does is it makes electrons. Let me make the electrons black, if I can find my black pen here. My black pen has gone bye-bye. Well, okay then. I'm going to make them violet. So it's going to make electrons go shooting down through here. And when the electron hits a molecule, it can excite the electrons in the molecule to a higher energy level. So the electrons have those energy levels that are actually shown here. And so the electrons that are bound to if it's a hydrogen gas, the electron bound to a hydrogen gas can be excited from its ground state up to a high energy state because an electron interacted with it, electron that came flying through. And so that was what was going on with this gas tube. Electrons were going through and making electrons bound to hydrogen atoms jump up to higher levels. But then, just like my example in class, when I put my shoes in the top level of the shelves, if I shake the shelves, the shoes will fall back down. And they're not going to land halfway between shelves. They're going to land on another shelf. Usually the ground, the bottom shelf, right? So the electrons can fall down, and if an electron falls from, n equals 6 down to n equals 1, using those energy calculations we did, remember, energy is equal to minus 13.6 electron volts over n squared. The energy going from n equals 6 to n equals 1 is a higher energy or then a higher frequency than what we can see with our eyes. So it's not visible. But if it goes from n equals 6 to n equals 2, then it gives us a violet light and we can see it. If it goes from n equals 5 to 2, 4 to 2, 3 to 2, those give us visible colors. If it goes from anything down to 1, even going from 2 to 1, that's still too much energy and we can't see it. And if it goes to any state that's not 2, notice the spacing of the bands. Because you're dividing by n squared, as n gets bigger, the spacings between them get smaller and smaller. And so anything that falls down to n equals 3 or down to n equals 4, those are too low of energy. Those are going to give you infrared radiation. So the only thing we can see with our eyes from hydrogen is things falling down into n equals 2. So in the lab, the last thing in the lab is actually a statistical calculation that shows you how temperature plays into getting that radiation that we can see. Well, historically, people only saw those, and Balmer, I can't remember his first name, found a pattern. He said that if he looked at it carefully, it looked like the wavelength of the emitted gas. So, oh boy. What he saw was not that. So is that right? Yeah, I believe that's the right equation. I didn't look it up beforehand. It's going to be coming up, I'm sure, in a couple slides, probably on the next slide. But Balmer discovered a mathematical relationship between the colors visible and just a counting number n. And of course, you note it has 4 there. 4 is conveniently enough 2 squared. And so I usually, instead of writing 1 over 4 here, I put 1 over 2 squared. And so we call this the Balmer series. That's how I remember his last name, because Balmer was the one who found this pattern. Well, then people started getting better light measuring devices, and they were able to measure the infrared and ultraviolet radiation. And when they started being able to measure the infrared and ultraviolet radiation, we have Lyman, who discovered that there was another series of ultraviolet light lines. And those ultraviolet light lines had exactly the same equation, except for instead of 1 over 2 squared, it was 1 over 1 squared. And so we have the Lyman series that is that. So that's the Lyman series. And then we have other people that got into the act. We have Paschen, Brackett, Funt, who noticed that there's infrared radiation that follows 1 over 3 squared minus 1 over n squared, 1 over 4 squared minus 1 over n squared. And that was understood before any of the stuff we've been talking about with energies of electrons was known. And so when Bohr came up with his Bohr model that said the energy of the electron had this form, then suddenly it made sense. Okay, E equals H. Actually, this has got to be 1 over wavelength. Because what it's turning out is saying, I didn't look at the equation beforehand. I'm pretty sure it has to be 1 over wavelength. Because what it's saying is the energy difference is equal to the energy that it ends at. Let's change that to final. Minus the energy initial. And using that equation there, and since E is equal to HF and F is C over lambda, so HC over lambda, that's why it has to be 1 over wavelength. Max has a question.
Is there any significance? Is that an R before the parentheses?
Yes, that R stands for the Rydberg constant. So R is equal to the Rydberg constant, which I'm not even going to worry about the value of it. It's just a constant. And using this equation here, you can say, okay, that's going to be HC over lambda is equal to minus, well, this last part is, that's substituting in. And so you can see that the Rydberg constant has to be minus 13.6 electron volts over HC. Actually, maybe it was initial minus final. I'm not going to worry about, I might have a minus sign wrong because the Rydberg constant is positive. But it's the idea. So we're not worried about the constant. What we are worried about is we now can explain where each of those colors comes from. It comes from the electron falling from one energy state to another, and all of the visible ones are falling down to n equals 2. Not to n equals 1, not to the ground state, but falling to n equals 2. Why not to the ground state? Because it gives you ultraviolet radiation if it falls to the ground state, too high energy. So here, no, I don't have it yet. This is showing a comparison between the lines for helium and hydrogen. And you see, now these two look pretty similar. They're not exactly the same place, but pretty similar. But this one has no counterpart. This one here you can see is offset a little more, no counterpart, no counterpart. That one doesn't match up with anything up above. They're different. And so we treat these spectra, we call it a spectrum when it's the different lines, it's a line spectrum. We treat these line spectra like the fingerprints of an atom. So you look at the emission lines or the absorption lines, because remember, absorption is once again going through the same energy states, it's just absorbing energy and going up instead of falling down and giving off energy. Those will tell us what atoms are present. So when you were here in class and I had the helium lamp, if you knew the energy spectrum for helium, you could have said, that's helium just by matching up the lines. And if I change it to mercury, you could have looked and said, that's not helium. It's something else you could have looked up and found, that's mercury by looking at the lines. And so you can do something else crazy, like take a mixture of gases and analyze it and break down this set of lines is hydrogen, this set of lines is helium, this set of lines is mercury. And so you can determine all the types of atoms present. Why is that? I see you have a question mark somewhere. Why is that important for astronomy? Well, once again, who here has ever been to, I don't know, the nearest visible star, not counting the sun? Alpha Centauri. Only Alpha's been Alpha Centauri. No one's been there. No one's able to go and sample and say, we have this kind of gas and this kind of gas. Even our sun. Now, we have had a spacecraft that tried to collect in an aerogel coming somewhat close to the sun, not anywhere close to being melted, but catch in an aerogel the types of atoms present so that we could study and have some direct physical measurement for the sun. But for something like Alpha Centauri, we have no chance of that. And so using this is the only way we can actually determine what kind of gases, what kind of atoms, molecules we have in other stars. Okay, Maxwell's question.
How are the spectra generated? Is it because why are they unique to atoms? Because each atom has different energy levels and different electrons in different places, and so is that it?
That is exactly it. You have to do some quantum physics calculations to calculate the energy levels of anything. Now the equation here that I wrote, that initially came from Bohr's model. But remember I said Bohr's model, this is going back a week. Bohr's model isn't our current understanding of the atom. Our current understanding is the quantum model. But the quantum model fundamentally agrees with the Bohr model in the energy states. Not completely agrees. We have spin states that cause some variations. We have things like the spin-orbit coupling, spin-spin coupling, relativistic effects, the fact that the nucleus is not an infinite mass. All of those things play in to give the Bohr model a slightly incorrect energy, but it's pretty small. But when you get to atoms that are bigger than the hydrogen atom, we use quantum calculations to calculate the different energy levels. And that's well beyond the level of this class to do those quantum calculations. And the fact is, the hydrogen atom is the only thing that we can solve completely. Actually, any atom that has only one electron, we can solve completely. As soon as you have two electrons, we can't. All right. So the key to this is every element has its own spectrum, so we can identify elements by looking at the spectra. So why in the world in an introductory astronomy class do we have to learn all of this stuff about quantum physics type ideas? So we see that there's a reason to have some confidence in the measurements that the scientists make. Now, the difference between an absorption spectrum and an emission spectrum is simply how you're observing. If you look directly at something like the sun, you're going to see mostly the incandescent light coming from the sun, right? You're just going to see the incandescence, which is approximated as a nice smooth curve like we saw in the pictures from last class period. But if there is a gas cloud between you and the sun, so this top picture here shows a gas cloud between you and the sun, that gas cloud is going to absorb some of the radiation from the sun. And so when you look at the spectrum through that cloud, you're going to see some frequencies where the light's been absorbed. Our picture makes it look like there's no light. Well, if you look at the upper spectrum, and I'll zoom in so you can see it better, say, oh, it's black, there's nothing there. Well, scientists actually don't look at the pretty rainbow colors. They use instruments to actually measure how bright it is. And you see that, these aren't going down to zero. That one was pretty close. But those are where the absorptions are, and they can measure how strong the absorption is to tell them about how many atoms there are that are doing absorbing. So to see the absorption spectrum, you have to have light coming from a bright object going through an intermediary cloud. If you want to see the emission spectrum, you do it a different way. Now notice this here is showing a continuous spectrum because there's nothing in the way. If you want to see an emission spectrum, and I'm pretty sure I have this on the next slide, but I'm still going to do it right here. If I put my eyeball right here, and I'm looking at this cloud, I don't see the sun behind it. So I don't have the continuous spectrum from the incandescence from the hot star. But I still have all of that gas that the electrons absorbed energy and went to higher energy levels, giving me the absorption spectrum. But what happens to those electrons when they're in the higher energy levels?
Come back down.
They fall back down. And when they fall back down, they give off emission spectra. The same transition, so the same colors, but now they're emitting light instead of absorbing light. So if I observe from the picture of my red eye there, I would see the emission spectrum from that same cloud. So if I'm looking with the star behind it, I see absorption spectrum. If I'm looking with black behind it, I see the emission spectrum. But there has to have been some hot source to do the excitation for me to see emission spectrum. Just a cloud with no hot source anywhere nearby, I'm not going to see anything. No, it wasn't on the next one. So we have three types of spectra we talk about in astronomy. The continuous spectrum from incandescence. Okay, that was beautiful. The emission spectrum that you see when you don't have a bright thing behind it, and the absorption spectrum when you have the bright thing behind it. And notice these lines exactly match up between the emission spectrum and the absorption spectrum. Both of those spectra tell you essentially the same information. Here is the sun's actual spectrum. I think this is the sun, yeah. So the sun's actual spectrum. The pictures I showed you before had nice, smooth things that would go like, well, not like that. Something like that. And here we can see it's not close to that idealized form. First and foremost, because we have air in the Earth's atmosphere that's doing a lot of absorbing. If we go outside of the air of the Earth's atmosphere, we'll see a more pristine spectrum from the sun. And if we go outside the Earth's atmosphere, we'll see the absorption from elements that are in the sun's atmosphere. And this is showing some of the primary things in the sun's atmosphere by their absorption lines. Now, those aren't the only lines. You see hydrogen here. Two of the lines were identified as hydrogen. Those aren't the only lines from each one, but those are what causes those different absorption lines. And so we actually, looking at the sun, we see those absorption lines, and they're full of information. I mean, at first glance, you look at that and you just think, it's bad data. It's not nice and smooth. But it's that what looks like bad data that's actually the important information. Now, looking at colors. This here is violet, blue, green, red. So the sun's peak in emission is somewhere here in the blue to green range. Nobody says the sun looks blue to green. But what you notice here is it's pretty close to constant there across the entire visible spectrum. pretty much what we identify as white. But then we have the Rayleigh scattering that takes away a lot of the red. So the Rayleigh scattering causes a lot of this to go down and makes it look more blue. Or excuse me, I said the other way around. Makes it look more blue. The sky looks blue. The Rayleigh scattering takes away the blue, and so it's more like this. It makes it look more red. Wow. I'm proud of myself. Moving on. Based on that information, this is what has been calculated to be the composition of the sun. The sun is, by number of atoms, 91% hydrogen. By mass, only 71%. Can anyone give an explanation why it's 91% by number of atoms, but only 71% by mass? Where's hydrogen on the periodic table? It's the first one. It's the lightest element. And because it's the lightest one, 10 hydrogen atoms has the same mass as, 2.5 helium atoms. And so it's a much smaller percentage of mass. And you look at helium. Helium is 8.78%. Add those two together, that's 99.89, basically 99.90% of the sun is hydrogen and helium. Just trace amounts of anything else. Then you get down carbon, nitrogen, oxygen, so on. Who knew the sun had gold in it? It does, not very much, but it has some gold in it.
It's gold everywhere.
There is. Now, as we'll learn with the whole nucleosynthesis thing, gold can only be created in the death of a supermassive star,
Supernova.
in a supernova.
So technically, that whole we could technically create gold, but it would be too long to actually do.
Well, we can't. Okay, back when I was a kid, I read the stories of alchemy and thought it must be possible, right? Because I was naive, just like the alchemists of old were naive. I thought that if you found the right recipe. I watched that Disney movie about the goose. Well, it's not the goose laid the old egg. I can't remember what the name of the movie is, but they have a wife who makes horrible, horrible applesauce, and the husband throws it away, and this duck eats it's a duck. The duck eats the applesauce, and it makes it lay eggs that are gold. Okay. I watched that, and I thought, there must be something to this. If you get the right chemical combination, you can make gold. Elements are not chemical combinations. You can't mix elements to make gold. What you have to do is change the nucleus. If you look back there, you see gold, that's AU for Erysium. It's down on the, I can't even see from here, I gotta get closer, 6. It's on the 6th row there at AU, a little bit right of center. Well, we could take something like, platinum, because that's cheap, right? No, it's not. We could take platinum and we could bombard it with things like neutrons or protons and hope to create gold. Or we might take iridium, osmium, those things are also very rare, and try to bombard them to make gold, but that's the only way we can do it, is by smashing things together. So you can take an atom smasher, which is incredible amounts of energy, try to smash things to make gold. It's always going to be a money-losing
No,
proposition.
that's what I'm saying. Like, theoretically, we could make gold, but it's just, there's no what's called real reason to make gold.
Yeah.
Because it makes so, yeah.
Yeah, it doesn't make sense to do it. Unlike making diamond. Diamond is not an element. You don't see diamond back there. Diamond is a chemical composition of carbon. Back when I was in graduate school, I had friends who were doing research to make diamond-like films. We couldn't make diamonds at that point. Now we can make synthetic diamonds. We can make diamonds that are perfect, and we can make them for a lot cheaper than the market price of diamonds because of the whole monopoly. And so the people who own the monopoly on natural diamonds try to make this bogus campaign about, perfect diamonds aren't valuable. It's the flawed ones that are valuable because those are what we dig out of the ground.
I mean, they never really were that, because they had the monopoly on them.
They're not that rare. It's a controlled market. Anyway, I don't want to have a political rant, so I'm going to move on. All right, now this is the piece for the next homework problem, the Doppler effect. I remember when I was 5 years old when we came to America, and my parents said, our kids have grown up in Sierra Leone and Liberia, and they've not even known Disneyland. We're Californians. And so they took us to Disneyland so, we could see it. And so, for a 5-year-old, Disneyland is awesome. And one of the things that really stuck out in my mind was the People Mover. How many people have been on the People Mover? As a 5-year-old, it was really fun. On the People Mover, they have, what it is just this slow little tram that takes you all around Disneyland so you can see the different things. But when you're going around Space Mountain, they have this section where they call it the super speed tunnel. And as you drive through, they put video on each side of your walls of cars racing past you. And they blow wind in your face. And they have the sound effects. So you hear meow, meow as the cars go past. All of those things to a 5-year-old were very impressive. And I was thinking, this is awesome. We have all these cars flying right by us. Well, I was wrong. There were no cars flying by us. But each one of those things was there to give you the impression. And the one that we're talking about here is the sound of the cars going meow, meow. Now, of course, as a 5-year-old, 7-year-old, 10-year-old, I tried to figure out what was going on with this. And I thought, is it possible that the cars are actually making different sounds as they're passing us? It doesn't seem to make sense. It seems like they would make the same sound all the time. And then when I got to high school physics, that's when we started learning about this, the Doppler effect. The Doppler effect is the effect that you have something that's putting off a consistent frequency. So think of it like a metronome. And every second, it's going tick, 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 tick. And the sound wave is then moving from that metronome toward you. But if the metronome is moving toward you, the space between the ticks as they travel to you is shorter because the metronome moved forward before it made its next tick. And so that means the wavelength, the space between the waves is the wavelength. The wavelength is decreased if it's moving toward you. If it's moving away, the space between the ticks gets bigger, and so the wavelength gets longer. Question marks.
But isn't wavelength and frequency, aren't they related together, and you can't change wavelength without changing frequency and vice versa? So
yes.
If the frequency stays the same, then how does the wavelength change?
Well, the frequency is changed because the wavelength has changed. So the frequency of the metronome going tick, tick, tick stays the same, but the frequency of the sound wave is higher than the frequency of the metronome. And that's what the Doppler shift is. So yes, it's not just the wavelength alone, it has to be both. And so the Doppler shift says if something is coming towards you, the frequency is shifted to a higher frequency. If something's going away from you, it's shifted to a lower frequency. Now, if we look at the spectrum of light, as shown here, red is on the low frequency side. So if something's moving away from you, the colors are all shifted to lower frequency, shifted toward red. And so we call it a red shift if something's moving away. If something's moving toward you, it's shifted toward the high frequency side of the spectrum. We call that a blue shift. So when we talk about Doppler shifts, we'll talk about a red shift or a blue shift. Red shift means it's going away from you. Blue shift is coming toward you. But we can actually do physics calculations for how the wavelength changes with the Doppler effect. And so this Z here is a number to typify the Doppler effect. And that Z is the shift in wavelength, that is delta lambda is equal to the wavelength observed minus the wavelength in the laboratory. So lambda 0 is the wavelength you have in the laboratory from some, like emission line. And delta lambda is that shift, the observed wavelength minus what it would be in the laboratory. And Z, your Doppler shift, is the ratio of the shift in wavelength divided by the wavelength. And it turns out that that shift is simply equal to the speed of the object divided by the speed of light. So if you calculate that Z number, the Doppler shift number, you can instantly calculate the speed because you have solved this equation for speed. Speed is equal to C. C is the speed of light in vacuum, which for us, we're just going to call 3.00 times 10 to the 8th meters per second times Z. Now, this equation is actually only true for non-relativistic motion. That is for things going less than about 1/10 the speed of light. For higher speeds, we have to use a different equation. But for our purposes now, that works. This is then another thing that we can determine about stars by looking at their spectra. What was the first thing we could determine about stars by looking at their spectra? The composition, the elements present. Now we have a second thing. We can determine the speed of motion. So now let's look at the homework problem and apply this. So that homework problem, which is way back here, okay, the homework problem says Mercury rotates at 3 meters per second at its equator. So if it rotates at 3 meters per second, what that means is if Mercury's rotating like this, things over here are going to have a speed of 3.0 meters per second toward us. Things over here will have a speed of 3.0 meters per second away from us. So that means that my Z is equal to V over C. If I want to compare my wavelength, I'm going to have both an upside and a downside. So I'm going to only calculate one side, and we realize it'll be the same number both ways. I'll have a red shift on one side and a blue shift on the other. This is a number, again, you should be able to do this calculation without a calculator. What's 3 divided by 3?
1.
1, yes. Now, we have that 10 to the 8 on bottom. If I have 1 divided by 10 to the 8, that's 10 to the 0 divided by 10 to the 8. We subtract the exponent 0 divided by, or 0 minus 8 is negative 8. And so this is equal to 1 times 10 to the minus 8. Now, that's a really small Doppler shift, right? But that Z, we said, was equal to the wavelength shift over the wavelength. And so my wavelength shift must be my wavelength, 10 centimeters, times 10 to the minus 8. Well, a centimeter is 10 to the minus 2 meters. So I'm going to do this in meters. So 10 centimeters is 10 to the minus 1. 10 to the minus 1 times 10 to the minus 8 is 10 to the minus 9 meters, or 1 nanometer. So that means my wavelength is going to be shifted up 1 nanometer on one side, down 1 nanometer on the other. So how wide would my line be if it's shifted up 1 nanometer on one side and down 1 nanometer on the other? Or answering. I'm going to draw a picture. This is unacceptable. Here is my 10 centimeters. And then I have down here a shift to 10 centimeters minus 1 nanometer. Is that a red shift or a blue shift if it's gone to a shorter wavelength? Shorter wavelength is higher frequency, so it's a blue shift. We also have the shift up here to 10 centimeters plus 1 nanometer. So what's the total width from there to there? What's the difference between 10 minus 1 nanometer, 10 centimeters minus 1 nanometer, and 10 centimeters plus 1 nanometer? 2 nanometers. So that line has a width of 2 nanometers, which is actually very easy to measure. So another thing we can determine rotation of an object by looking at the width of the lines with the Doppler shift. Now we're going to learn later, we also can tell about the size of an object by the width. Really large objects, the molecules in the atmosphere are not having many collisions, and so they have very narrow lines. Small objects, you have a lot of collisions in the atmosphere, and that broadens the lines. But these atomic emission lines or absorption lines tell us huge amounts about the stars we study. Okay. Yeah, as I said before, the number 9 is just a math problem. It's what is 1/10 of visible light? What is 1/10 of radio light? What's 10th of gamma? Right? Those aren't very hard calculations. Just take the typical wavelength. There's a range, so just take something in the middle, divide by 10, tells you how smooth something has to be. But then you have to match up objects with physical sizes. So number 9 is just a math problem. Remember 7 and 8, those are relativity. And number 10, we will answer. Number 11 is, again, just a math problem. How's 10 to the 4th compared to 5 to the 4th is what's asking. What's the ratio of those two? That's all it's asking. So those math ones I'll leave to you. So I'm not going to come back to do any problems unless we get to telescopes, which I don't think we will because I want to end the lecture pretty soon rather than lecture for more than anybody's attention span can handle. Okay, so we've talked about the Doppler shifts and the differences they cause. We're going to see that this played into Edwin Hubble's discovery in a very major way. So other measurements that the Doppler effect affects, we just saw that you can determine things about the rotation rate of objects, right? That's what the homework problem was dealing with. The motion of stars in a binary system, that is, as the stars orbit around each other, you have this star's coming toward you at a speed, that one's going away from your speed, so you can determine the speeds they're moving as they orbit each other. The annual variation Doppler shift provides evidence for motion of the Earth around the sun. Yeah, if you're a flat earther, you got to throw that one out. And then here's one that just makes me sad. Police use this same effect to say, you, sir, we're doing 80 in a 60-mile-an-hour zone. Pay me $200, please, or whatever the fine is. Okay, it's a practical application of using this. I would much rather keep it into the science realm and not have it affect my wallet. At the same time, I should probably be responsible, follow some laws with driving. So the Doppler effect, really important in astronomy. That's why we talk about it. All right. Clicker question. It's been open the entire class period. When observing a distant star, you notice that there is a series of absorption lines that match those of the hydrogen-Balmer series, but are all shifted a little, slightly shorter wavelength. What does that tell you about the star? Excuse me? I'm going to look for anyone who answers number 4.
Oh, now you make me want to press number 4.
Don't do it.
But it seems so right.
I had an answer in my physics class that was, it's done by magic, and one student chose it.
If you ever do that, that's how I'm going to answer it. I guarantee you.
Yes. I once joked in class that we explained a physical phenomena with magic. Physicists were just masters of prestidigitation. For the rest of the semester, since we're throwing that back at me. Okay, we have a couple people changed their answers right at the end to the correct answer, I might add. 8 and 4. I am going to have whoever's name is on this card. Gabby, except for I wrote this before I knew that she spells her name with an I instead of a Y. Gabby, explain first your answer and your justification.
So I said 2.
Okay.
And I couldn't remember what you said about that. But I was picturing the picture.
Mm-hmm.
And I remember seeing, the blue is on this end, and that's the one with the shorter wavelength. And so it was going towards it, and that was my only guess.
And that's a perfect answer. Okay, so it was a guess based on your recollection correctly of what you just saw. Of course, it was based on recollection of what you saw, not what I said, but you know what? The goal here is for you to learn, not, remember everything the teacher says. So that's great. Okay, so she was absolutely correct. If it's shorter wavelength, then it's gone toward a more blue color, and blue is coming toward you. So that was the correct answer. Okay, now we have our section on telescope, and I'm just going to say the telescope for tomorrow in class. So I definitely will take out, now that I've gotten this far, I will take out the relativity problems on the homework. So they're the 2 in the, 8 or 9, something like that. I'll go back to. There we go. So, nope, it was here. So I will be taking out 7 and 8. So you don't have to do those 2 because we just haven't covered them. Won't have time to cover them before it's due. We still have to talk about this telescope question that we'll cover tomorrow in class. Okay, let's take about a 10-minute break. So reconvene about 9:10. And in that time, I will get our experiment, or our little lab thing ready. And I'll stop the recording.